Okay, so let's take a look at how we are going to achieve this trade-off between complexity reduction and variety retention or variability retention. So we are going to do that by evaluating the quality of clustering. Okay, so reducing complexity is very clear. The complexity is measured by the number of clusters. Right? So you've got 10,000 customers, you want to treat it as if there are only 15 customers or 15 clusters. So that's the number of clusters tells us the complexity reduction. But how do we retain variety? Right, till now I've been talking about it only intuitively, but how exactly do we measure the variety available in your data? And we want to retain as much of it as possible. So for example, suppose this is our data set, right? The same data set, age and height. You've got, this is the mean, right? And of course, we've already spoken about the fact that we measure variety by the sum of squared deviations from the mean, right? So for example, here's the age, this is the mean age. For every age, I want to find out age minus mean, the difference of a particular age from the mean, and square it. Sum of squared deviations from the mean, or what we had earlier called in linear regression as total sum of squares. Okay, so for age, the amount of variability in age is measured by the sum of all of these. Right, you add up all of these, you get the amount of variability that exists in age. Similarly, for height, you do the same thing. Square of height minus mean. That is the sum of squared, total sum of squares for height. Okay, so there's so much variability in age, there is so much variability in height. This is the total variability for every case, right? So for this first case, the total variability is this plus this, right? And across the entire data set, the total variability is the sum of all these numbers. Okay, and therefore, in this data set, the total amount of variability that exists is 806.8. Okay, and when we do a clustered solution, we want to see what percentage of this our clustering still retains, right? What we would like to do ideally is to try and keep as much of this variability as possible while reducing the complexity and saying, okay, I'm going to treat it as just two clusters. Well, if it's only two clusters, there's going to be some loss in variability, but how much is that? That's what we want to find out. Okay, so just make sure you understand this notion of the variability, right? So take a look at this calculation, that calculation, and sort of internalize what's going on here. Don't look at it as just some numerical calculation, but look at what it means, right? So when we do this, what we are saying is for every value, we are seeing how far away from the mean it is. In other words, what we are saying is we are getting a measure of how much of spread these values have. Okay, earlier you did that through the measure called standard deviation, but here we are doing it just by taking the total variability. We are not interested in dividing by n or anything like that. Okay, so that's what we are getting here. Okay, so what happens is when you divide, suppose this is you've got a data set, right? For example, the previous data set. We already calculated that the total variability there was 806.8. Okay, so let's say that this is that data set and X happens to be that 806.8. Now suppose you take this data set and divide it into two parts. In other words, two clusters. Doesn't matter how you do it, just break it up into two parts and calculate the variability of this part. Let's say that turns out to be A, and calculate the variability of this part that turns out to be B, right? Obviously, what you'll find is that A plus B does not add up to X, right? That is because when you're talking about X, you have one average for the entire group, and there's going to be a lot of variability around that particular average. If you break it up into two small groups, okay, you've got two different averages, and each of those averages is somewhat closer to the cases on which that average is based. Okay, so therefore what is going to happen is that the total variability here is going to be less than this. Okay, so you will find that a plus b is generally less than x. In some extreme cases, with the data constructed very carefully, hand constructed, a plus b might be actually equal to x. For example, if all the values are same in all of them, of course, then the variability will all be 0. But other than that, in normal cases, you will find that when you create clusters, you're reducing the total amount of variability. Okay, so let's measure the incoherence of a cluster. Okay, so clearly we have said cases are similar to each other, which means that they are close to the mean of the cluster. Okay, so that's your cluster 1. And the measure, of course, as we've already seen, is the squared deviation from the mean. You can calculate that as we've already shown you. For example, the mean age is this for the cluster. Now, this mean is not the overall mean, it's the mean for the cluster. So you take every value, divide, subtract from the mean, square it, right? So this is the squared deviation for age, that's the squared deviation for height, that's the total amount of squared deviation for this particular case. And you do it for all the cases. Okay, now again the problem here is that you find that heights are measured in much larger units than are ages. Okay, the numbers, the absolute numbers of heights are much larger. Therefore, when you calculate the total sum of squared deviations, heights will tend to dominate. Right? This will not play much of a role, as this plays. Okay, so again, remember when cluster analysis, you're talking about similarities, and similarities mean distances. What do you mean by saying all these cases are similar to each other? Well, similar to each other in terms of distance calculations. Okay, and therefore, as we've already seen with k and n, you will have to scale the values. Okay, so in cluster analysis, you don't work with the original data. Instead, you normalize the data, and then you perform cluster analysis on the normalized data. Otherwise, some attributes may dominate your clustering. That may not help very much. Okay, so the moment you're talking about distance being used as a measure of similarity, you end up with the need to normalize the data, just like we did with k and n. Okay, so let's use our method to now calculate how much of incoherence is there in cluster 1. Okay, so here are the standardized ages and the standardized heights, right? Remember we said that we need to normalize them or standardize them. That's what we've done. Okay, and here are the mean and this mean of the standardized age and standardized height. Okay, now why are these values all negative? That is because in cluster 1 you have people whose ages are smaller and heights are smaller, right? So they are all below average, and therefore when you standardize it, anything below average becomes negative. That's what has happened here. Okay, now of course when you calculate the squared deviations, all those negatives vanish. This is squared deviation of age, which is this value minus the mean squared deviation of height, etc. So when you calculate the measure of incoherence of cluster 1, you get this number 0.9567. Okay, this is called within sum of squares, right? That is, this is the sum of squared deviations for the particular cluster. That's why it's called within the cluster. Okay, so this is called within sum of squares. Sum of squared deviations just for the cluster. And this is the within sum of squared deviations for cluster 2. Okay, so now remember, this is the measure of incoherence of the original data. Remember, we calculated it as 800, but that was with values when we had not scaled or normalized the heights and ages. Here we have normalized the age, normalized the height, and we are doing exactly the same calculation. Only thing is, this is the entire data without any clustering. Okay, and that is called as total sum of squares. That is the amount of squared deviation or variability that exists in the total overall data. Okay, that's called total sum of squares. And in this case, that happens to be 22. Okay, so the total sum of squares is 22. And the sum of squares of the two clusters are close to 1 each, right? The sum of squared deviations for the two clusters, they add up to close to 2. Okay, so in coherence, the original data was 22. Incoherence in the two clusters is about 2. Okay, so we've got a massive reduction in the incoherence, right? Each of our clusters is extremely coherent. There's a lot of incoherence in the original data. We've reduced that. Okay, and we've also reduced the complexity from 12 cases down to 2 cases. Okay, so we started with 12 objects. We are now with 2 clusters. 6 of them having this mean age and this mean height, and 6 of them having that mean age and that mean height. Okay, now don't get worried about the fact that these numbers are actually the same with reverse signs. That's just what happened with my data. This was handcrafted data, so it just came out like this. In general, it won't happen like this, right? And also another point, the number of cases in each of the clusters need not be the same. Okay, this was just simple data set that I had created to illustrate cluster analysis, and I just happened to create equal clusters. That's all. Okay, so let's look at how much of the variance was retained. Okay, now remember what I told you earlier is that the moment you've done clustering, right, this is one cluster, that's another cluster, you're going to treat the cases as if all the cases in each cluster are identical, right? That's the whole idea. You want to reduce complexity. You're saying, instead of seeing 12 different objects, I'm going to just think of it as 2 clusters with each cluster containing identical objects, which is based on the average of the values in each cluster. Okay, so therefore what you have is there are 6 cases of this cluster 1 and 6 cases of this cluster 2. Okay, so instead of thinking of them as 12 different cases, which was the original data, I'm thinking of it like this: 6 of identical cases and 6 of these identical cases. Okay, now if I measure the sum of squared deviations for this new set, the mean of course will be 0 because these are all standardized, right? So now if you calculate the squared deviations, I'm getting that the total amount of variety in this data is 19.96. Okay, now remember, the total sum of squares in our original data was 22. And total sum of squares in our clustered data is 19.96. Okay, so we managed to reduce the complexity from 12 objects to 2 clusters, but still we managed to retain 19.96 of the total SS of 22. Okay, so even though we reduced from 12 objects to just 2 clusters, we are still keeping 90% of the variability that exists in our data. Okay, so that's a good measure of how good the clustering is. Okay, of course, you can retain 100% of the variability by treating every object as its own cluster, right? But in that case, you don't get any complexity reduction. Here, what we have done is we've got a massive complexity reduction without much loss of variability. There's a very small loss of variability, but it's not at all much. Okay, so that's an example of a very good clustering solution. So let's come back to this question of how do I know how many clusters I should create? Okay, the way we are going to do that is the following. As we already saw, every time you increase the number of clusters, your error is going to keep on going down, right? That we saw, because every cluster is going to have its own mean, and if you take the sum of squared deviations from the mean for every cluster separately, that's going to be less than what you get for the total data set, right? So as you keep increasing the number of clusters, your total of all the within sum of squares for each cluster will keep on going down, right? So this of course is 22, which is the total sum of squares treating all the data as one cluster. That's what you get. But the moment you go down to 2 clusters, right, your total sum of the within sum of squares for each of them, if you add up, it comes down to about 1. And then it continues to keep on reducing further and further and further. Okay, now this gives us an idea of at what level am I getting the maximum benefit from clustering, right? So where you see a steep drop in the total error, in the total of the within sum of squares, that would be a good point. So in this case, you see a massive drop from one cluster to two clusters, but after that, the drop is pretty gradual. Okay, so you may say that by going from two clusters to three clusters, I'm not getting that much of a benefit in terms of reduction of the total deviation. Okay, and in this case, we already saw that by going from one cluster to two clusters, you reduce the complexity without sacrificing much on variability. Okay, so in this case, you may say, I'm going to choose two clusters. Okay, but of course, everything being said, it is still a subjective decision in terms of what what you're looking for. Okay, so that's a single cluster with all cases, and that's close to each case being in its own cluster. We have 12 cases, so it cannot be 10 clusters, but I just stopped the plot at 10, right? So the 12 would be somewhere here, but this is close to that. Okay, so this is the approach we are going to use to find out how many clusters to actually have.